Good afternoon, everyone. Welcome to another seminar of our cycle of seminars of the Astronomy Department of the IAG. Many thanks for joining us here, or if you are following through our YouTube channel. And today's speaker is Dr. Jacob Crossett. Many thanks, Jacob, for accepting our invitation to be here today. Oh, sorry. I have a problem with my YouTube. Yeah, I'm sorry. So I will briefly introduce Dr. Crossett, who got his PhD degree from Monash University in Melbourne, Australia. He then worked as a research associate at the University of Birmingham, and currently Jacob has a Fondesit fellowship at the Universidad de Valparaiso. And his research focuses on the role of galaxy environment in changing galaxies from blue star-forming spirals into red passive ellipticals. And today, Dr. Crossett is going to talk about understanding the evolution of galaxies in dense environments and the search for jellyfish galaxies. So please turn off your microphones and your cameras during the talk. And if you have a question, you can raise your hand here in the Google Meet, or you can write it down if you're following in the YouTube. So you can write it down in the YouTube chat. And we will ask the question after the presentation. So that's all. Jacob, whenever you are ready, you can start sharing your presentation.
All right, thank you for the very lovely introduction. I'll just make sure I share the entire screen exactly the right way. I don't want to get it wrong. So hopefully we can see the full screen of the presentation. Is that all good?
Yeah.
And my cursor as well, you can see that darting around just in case we need it for later.
You can play a little bit more with it. Yeah, we can.
Excellent. Okay, thank you. All right. Well, thank you very much for the introduction and giving me this opportunity to speak to you today. So my name is Jake, and I'm going to be presenting some of the work I've been doing recently, predominantly here in, well, where I normally work in Valparaiso, Chile. And thanks, of course, to the people who I've listed here below, who have been really pivotal in helping some of this work to come to fruition. Now, briefly about me, as we sort of already alluded to in the introduction, I grew up and studied in Victoria in the south part of Australia, as you can possibly tell by my accent. I did my PhD mostly in Australia, but took a brief sabbatical to the UK. After my PhD, I was lucky enough to go back to the UK and get a postdoc at the University of Birmingham, as you can see in the photo in the bottom of the three. I worked there for 2 years with Dr. Sean McGee. And then since about 2020, so just before the pandemic hit, I've been working in Valparaiso, Chile, working with Dr. Jellyfish, trying to find and study the evolution of jellyfish galaxies and ram pressure stripping. So to give a bit of an overview and go back to the basics about what I'm interested in, what I really care about is why we see differences in populations of galaxies. So I've got a couple of pictures of two galaxies here, and what really sort of drives what I want to do and what I want to know is sort of why do we see these differences in these galaxies, and how do these galaxies change between each other, and what causes those kind of changes? So to sort of catalog some of the basics that we see of these archetypal galaxies, which are very common sort of in the local universe and at low redshift. We've got at the top these elliptical galaxies. These sort of elongated football-shaped sort of galaxies look, as we can see, red. They seem to have a big bulge, and they don't really have much going on in the way of star formation. There's no knots of new stars being born. They also tend to be quite high in mass and tend to be dominated by sort of dispersion. Conversely, at the bottom, we've got a picture of the other sort of major type of galaxy we see around the local universe, and that's the spiral galaxy. Now, these galaxies tend to be blue with lots of knots of star formation, as you can see in the picture here, and then sort of dominated by that large disk that we can see going across this. So these are the major types of these galaxies, and we've got a bit of a dichotomy already, and we say, well, what causes this and how do they relate to each other? Now, interestingly, these galaxies also sort of exist in different parts of the universe. So we see as it tends to be, these are all, of course, generalizations, and there are exceptions to all these rules, but the spiral galaxies tend to reside in these low density regions, so it's sort of more on their own without lots of galaxies around it. And conversely, the elliptical galaxy, the one at the top, they tend to reside in very dense environments. You can already see in the picture I provided that there's a whole bunch of little galaxies sort of around it, and that these galaxies sort of sit in these clusters of galaxies, of many hundreds of galaxies, all within a small region of the sky. And sort of what I'm interested in is sort of how do we get these galaxies transforming from one to the other, and how do they relate to each other? Now, there's a few sort of pictures of how this might happen. We know that we've got a blue and a lower mass, so smaller in terms of how many stars are in the galaxy, spiral galaxies that we think form stars, and something like a collision might happen between two of them. That will mess up that spiral morphology, cause all the star formation to go off at once, and then we'll form sort of a big elliptical galaxy, these higher mass elliptical galaxies, which will then sort of run out of gas and then sort of passively evolve. And that's sort of one of the main pictures we think of when we overgeneralize how these galaxies sort of evolve. However, exceptions are very obvious. We can think back to even our own Milky Way, or one of our closest neighbors, the Andromeda galaxy, where we see that these galaxies are sort of larger spirals that have already lost their star formation. So both the Milky Way and the Andromeda tend to have lost a lot of the young stars already and are sort of declining in that star formation rate, which means that this picture of two gas-rich galaxies colliding and then forming ellipticals is not always true, and that there's a few different ways that these galaxies can sort of go from one start point to that sort of end point. So we've got a few different scenarios which these galaxies can sort of move between each other. Now, there's a lot of ways in which we can do this. So I've sort of given a couple of examples before, but there's a lot of different processes and things which cause these galaxy transformations, and how these galaxies can interact with each other and change and evolve over time. Now, this is taken from a review by Comedy and Kennicott, which sort of categorizes a lot of the known processes and a lot of the ways that these galaxies can transform. And it's divided in this square, with the top being some things, fast processes, which sort of happen very quickly, like quicker than either a cluster crossing timescale or a dynamical timescale of the rotation timescale, or just it happens generally quick in a cosmic term. And then the bottom are the slow, or sometimes called secular processes, which take a lot longer cosmically compared to the other ones. And then left and right, we can look at things that happen sort of within the galaxy, such as the morphologies, such as bars and spiral structure, changing how gas is distributed, or things on the right-hand side, which is other galaxies and other mechanisms acting on the galaxy. And it's this right-hand side, which is what I'm really interested in. How does a galaxy's environment, or the area of which it resides, change how its properties and transforms galaxies? Now we can see here there's a whole host of different kinds of processes which can transform the galaxies. And there's a lot of evidence to suggest that galaxy environment does transform galaxies. Here's a few I've cherry-picked from several different results. We see on the left-hand side that if you go from sort of low density on the left of the plot to high density on the right of the plot, so just less galaxies in space to more, we see that the fraction of spirals drops down from sort of a high fraction of the population to a low, and conversely, those elliptical galaxies, those sort of more passive galaxies, sort of increase as we go to more high density regions. In the middle, we see that if we have a distribution of the star formation rates, how many stars are being made over a short amount of time, we can see that the distribution of star formation rates drops as you get closer and closer to the center of these sort of dense structures that we're speaking about. And then on the far right-hand side, we can see the changes in different colors of galaxies. So that's just a ratio of the blue light in a galaxy and the red light in a galaxy to create sort of a color and a flux ratio, if you will. And we see that the closer you move to these sort of dense structures, we get more and more red things and fewer blue things. So we sort of see this transformation as we go to dense environments, from being these young star-forming spirals with blue colors to red and dead elliptical looking galaxies in these dense structures. Now, what do I mean by dense structures? So the archetypal kind of environment or dense structure we're speaking about is always the galaxy cluster. Now, this is a large gravitationally bound structure of hundreds of galaxies, all sort of within close proximity to one another. Now, as well as the galaxies, accreted gas and things can come into the cluster and then be heated up through the gravitational potential well as they're accreted, and they emit sort of a hot plasma. Now, this hot plasma can emit bremsstrahlung radiation, which allows us to observe this intra-cluster medium, this sort of hot plasma around these through this galaxy cluster. We can observe this through X-ray emission, so we can sort of see this as well. And these galaxy clusters provide a really good way of viewing a lot of the processes which can happen, these environmental processes which can change change galaxies within them. So we have these dense environments which change galaxies from that blue to red, but what are some of these processes that do that? So some of the most obvious ones that people can think of are gravitational interactions. So the quintessential one is the merger. So two galaxies, as they come in, they sort of collide and then sort of coalesce or merge to form one new item. We've got a lovely picture of the antenna galaxy here on the left, showing sort of a major merger of two similar sized objects. Now in clusters, because the potential well, this gravitational well is so large, the galaxies actually move very fast through the cluster, and the galaxies, the relative velocity, so the speed between the members, is such that the galaxies actually won't collide and then come back and join to form one object. Instead, repeat flyby interactions, so just purely passing gravitational interactions, can contort the morphologies of galaxies, the shapes of these galaxies, such that they still can be transformed. Now, repeated flyby interactions happen approximately once per gigayear per galaxy in these clusters, and are termed collectively as harassment. And we can see here on the right, this image of NGC 4438 looks very similar to the simulated galaxy in the bottom, which has had these sort of repeat interactions. Now, in addition to interactions of galaxies, we also have interactions between a galaxy and the intra-cluster medium, that hot plasma that pervades galaxy clusters. This occurs when a galaxy folds into a cluster, and the gas within the galaxy feels a pressure and a wind from the intracluster medium. And this hydrodynamical interaction between the intracluster medium and the gas within an infalling galaxy causes the gas to be heated up and often stripped out of the galaxy. This can then mean the galaxy has been depleted of its gas and can't form new stars, and such it'll sort of finish its star formation and become a lot more passive. Now, I've spoken mostly about galaxy clusters, but this is not the only kind of environment. In fact, in the local universe, the modal or the most common sort of environment for a galaxy to reside in is actually termed a galaxy group. Now, where a galaxy cluster is sort of hundreds of members large, galaxy groups are usually on order of a few tens of galaxies. So they're basically a smaller cluster. They work in similar ways. They still are, it's an association of galaxies together, and there is an intra-group medium, so intra-cluster, intra-group medium, but the same kind of idea. However, because these are smaller, the relative velocities between the galaxies are smaller, such that interactions and full mergers are more likely, as we can see in this image here on the right of Cepheid sextet. And the smaller total mass means there's less of a potential well to bring that intra-cluster medium and make it more dense, which means that ram pressure may not be as effective in groups as we see in clusters. Now, galaxies tend to form in groups, and then these groups themselves can then be accreted onto a cluster. And so we think that the groups themselves may do a lot of the heavy lifting, if you will, of quenching galaxies and forcing those to become passive and quenched. And we term this pre-processing. This is when galaxies are sort of quenched and transformed in a group environment before that group is then accreted into a cluster. We can see this in this figure here from Bianconi, I believe it actually now is accepted in 2018, so apologies for that, showing galaxies that have known substructures, i.e. that have fallen into a cluster via a group in the black triangles, and they seem to have a lower fraction of star-forming galaxies than the other cluster members at similar radii. So that this seems to show that galaxies that have fallen into a cluster via a group environment seem to have lower star formation and that have been sort of already transformed or pre-processed. So we've seen already now that both groups and clusters can sort of cause these transformations and changes in galaxies. But there's still several open questions about how this all works and what takes place where and things. Now, I've cherry-picked a few questions that I think are very interesting, such as, do we see similar kinds of transformations in both groups and clusters? And how do the galaxies change if the groups themselves have changed properties and themselves have formed more or evolved more? And these are some of the questions I'm going to hopefully speak about in my talk. So for the rest of the talk, I'm going to focus on a few of these questions that may be foreboding with a few answers that maybe are in these sort of papers. And these three main results are sort of what I'm looking at. The first one we're looking at is linking the formation of the group to that X-ray emission from that intra-cluster medium. Second part I'm going to look at is looking at RAM pressure stripping, and do we see that in group environments as opposed to those larger clusters? Finally, I want to investigate the idea of using citizen science and other ways of looking for large samples of RAM pressure strip galaxies to learn more about these sort of transforming objects. So for the first part, what I'm really interested in is if we take two groups of sort of similar size with similar numbers of amounts of members, why do some groups have a really strong intra-cluster medium, whilst other groups seem to be almost devoid of any intra-cluster medium at all? So we see that some have strong X-ray emission from this intra-cluster medium and some just do not. Now there's a few theories about why that is, including differences in the group age or formation time, different properties of the intra-cluster medium, including changes in the entropy or the way the group formed. But it's also murky a little bit by how we select groups, and things like line of sight filaments and that can sort of murky those waters. But I think it's still quite an interesting question on why we see some groups that seem to have this stronger intra-cluster medium than others. But to look at this on a big statistical level and on a large sample, we need to have sort of a lot of data. And what we need to have is a catalogue of groups that we can use as a seed, but then we have to be able to detect or at least measure the X-ray emission in all of them. Now, previous results have done this, tend to use only shallow X-rays. And often when groups have not been detected in X-rays, they just sort of are left out. We can't really analyze them. However, recently, I've been able to use data from the Galaxy and Mass Assembly Survey to get a large sample of spectroscopic friends of friends groups. So these are sort of a highly complete data set of groups of galaxies which all have spectroscopic redshifts, which means we can sort of measure the positions of them quite well. Now, I've been able to couple this with X-ray data from the XXL survey. Now, this is a survey that used two areas and just took X-ray sort of photometry across the whole of these sort of areas. Now, as it so happens, one of the fields of GAMA and one of the fields of XXL overlap significantly. And we can see this in the figure on the right. The squares with the green squares in the figure show the high completeness areas of the GAMA survey, where the spectroscopic completeness is very, very good. And the yellow outlines show the XXL footprint. And you can see there's a beautiful area where we have a high completeness optical spectrophotometric data with X-ray measurements throughout the whole region. This has allowed me to investigate the properties of over 200 galaxies that have been optically defined and measure the X-ray fluxes. Now, to measure the X-ray fluxes, what we've done is we've taken the optical group, the optical center of the group, and then performed 300 kiloparsec force photometry on each of the group centers. So we're not sort of measuring the contours and getting a full APEC model for each. We're just sort of forcing the count rates on each individual spot. And then the photometry, the count rate we get, we then model that to get an X-ray flux and then an X-ray luminosity. So this way, we're getting an X-ray measurement for every optical group, regardless of if there's a source or not. Now, the Bayesian method that we use to do this is from Willis et al. And the posterior distribution actually allows us to get upper limits when there is no flux within the aperture. So we actually have upper limits as well as measured groups. Now, we've tested that this agrees with existing data. So there's a small overlapping subset with other XXL data from Adami et al. 2018. And what we can see is for almost all the groups, the X-ray, the 300 kiloparsec aperture photometry, that luminosity matches the R500 Adami et al. Luminosity as well, and almost always very close to a 1-to-1. Now, in a few cases, you can see they're quite divergent between the two of them, but those cases, what is occurring, you can see from the color bar, is it's often the case where the XXL existing source and the gamma center are just very far apart. And so the reason for the discrepancy is that they're just measuring different parts of the cluster. So we've fixed those up and sort of moved them to the correct center. And that's the reason that those ones sort of are somewhat discrepant. So we're pretty confident that this photometry is pretty reasonable and pretty accurate with other published X-ray photometry. But now we've got that, we can sort of make a diagram of optical luminosity against the X-ray luminosity of all our groups. And as you can see in the figure here, there's a lot of scatter between sort of the brightest and the dimmest. You can also see in the figure the little down arrows, which show the upper limits where the groups didn't have any measured X-ray photometry, but we have a 90th percentile upper limit for all of the ones where we couldn't get a peak for the posterior distribution. So to analyze these groups and have a look at why we see some that are really bright and some that are really quite dim, we divide our sample into three little subsamples. We've got in the blue the groups that are X-ray overluminous, that have a high X-ray luminosity for its optical luminosity. And in the red, we have the X-ray underluminous, the ones that are quite faint for their optical luminosity. We make some cuts in redshift and optical luminosity to sort of get the samples to be about the same in terms of number and in terms of sort of the range of parameters such as multiplicity. But we do note here that the red points, the underluminous, are slightly larger in optical luminosity, so a slightly higher mass than the overluminous ones. Now, when we investigate the structural parameters of these galaxies, we find that when we investigate the offset between the brightest group galaxy and the optical group center, i.e. how central is that central galaxy in the group, that the overluminous groups have a more centralized BCG than the underluminous groups. We can see that in the right-hand panel, the normalized distribution on the right shows that the blue curve of the overluminous group seems to have a lower log BCG offset. And we can see in the top panel, the three stars show the mean for the entire sample. And the two lines show the mean in sort of the upper half and the lower half bins. So we see on average that the BCG is sort of more centralized in the overluminous groups. Additionally, if we look at the magnitude gap, i.e. how big is the BCG compared to the next galaxy, we find that across the entire sample, seen in the top panel, and a little bit in the distribution on the right, that the overluminous groups have a larger larger central galaxy. So that BGG, the brightest group galaxy, seems to be more dominant in the overluminous groups than the underluminous groups. Additionally, if we look at the fraction of galaxies that have a higher star formation rate, or a blue on the color magnitude diagram, have that blue ratio between red and blue fluxes, we find that the overluminous groups have a lower star forming fraction. So there are fewer galaxies with high star formation rates and fewer galaxies that are blue in the overluminous groups compared to the underluminous groups. So we see that the overluminous groups have these bigger BCGs that are more centralized and fewer blue star-forming galaxies compared to the underluminous groups. We also see that if we were to sort of take a quick survey of which galaxies have more sort of irregular morphologies, be it sort of mergers or maybe features for ram pressure stripping, that the overluminous groups tend to have fewer galaxies that have those kind of merging morphologies or even ram pressure stripping features. So these two luminosity, optical luminosity, X-ray luminosity plots show that the fraction of galaxies with a merger or RAM pressure stripping features tend to avoid that sort of upper part, the overluminous subsample. Now, this is still a bit of a tentative result, and this result itself is not published in the paper that has been already published. So these are a little bit tentative still, but are working on in the future. But taken together, what we can say is that the overluminous groups seem to have a higher fraction of sort of red and passive galaxies compared to the underluminous sample, and that they've got a larger BCG that's more centralized compared to that underluminous groups. So taken together, we really think that that means that these groups have formed earlier. So they've had more time to sort of have their BCG accrete mass to move into that center of that potential well, and all the galaxies within the group just start sort of losing their star formation, becoming passive. So whatever's done to transform these galaxies has had more time to do so, whereas the underluminous groups are still in the process of forming. There's more mergers because they're still sort of coming together and becoming a group, and that's why they still don't have that strong intra-cluster medium. Now, I just still want to circle back a little bit to the RAM pressure strip galaxies and how I mentioned that there were fewer of them in the X-ray overluminous groups. And this was a little bit of a surprising result because a stronger X-ray flux would suggest a stronger or more dense intra-cluster medium, which is very important for RAM pressure stripping. So I want to explore this idea of RAM pressure strip galaxies in groups a little bit more. So as a bit of a primer, we'll go back and we're going to look a bit more in detail about RAM pressure strip galaxies. So again, as we said before, it's caused by the hydrodynamic interaction between the gas and the galaxies. And this hydrodynamic wind, if you will, of RAM pressure as a galaxy enters a cluster forces the gas to be sort of stripped away. And we can see several examples of these here from galaxies in the Virgo cluster, where the H1 contours, so this is the neutral gas, seems to start to be pushed away and out of the galaxy. And in one case, in this bottom left image, it seems like the gas has actually been completely stripped out and the galaxy has lost a lot of its gas. So it's been sort of truncated into only just a small little well in the middle of the galaxy. So this is sort of the telltale signs of RAM pressure. Now, the equation we use to sort of understand RAM pressure stripping is given here, and it's taken from Gunn and Gott in 1972, where the RAM pressure depends on sort of two variables. The first one is the density of the medium, in this case, the density of the intra-cluster medium. And the second one is the relative velocity between the galaxy and the intra-cluster medium. So the faster the galaxy is moving in, the more it feels it. And it's the velocity squared. So it very much depends on the velocity of the galaxy. Now, if this RAM pressure is higher than the gravitational binding from the galaxy, the gas will then be stripped. Now, once the gas is stripped, we can actually see the signs of this RAM pressure in a whole bunch of other bands. I've got several examples here, including the H1 we saw before. And as well as that, the gas can start to condense and form new stars. And these new stars can be visible in optical imaging, as well as can ionize the gas around it, causing an emission in H-alpha. Additionally, the galaxies, these stars can sort of form and die, and all these new stars can then, in the supernova explosions, can emit cosmic rays, which themselves get stripped out as the galaxy moves into the cluster. And we see that in the bottom right image there from the Coma cluster. And finally, the interaction between the cold gas of the galaxy and the intra-cluster medium can cause the gas to excite and be visible in X-rays as well. And we see that in the bottom left here. So there's a few different ways we can visually see these signatures of RAM pressure stripping. Now, RAM pressure strip galaxies tend to have some interesting properties. We can see on the left here that RAM pressure strip galaxies tend to have higher average star formation rates than galaxies that are not undergoing RAM pressure stripping within clusters. And additionally, we've seen that a lot of RAM pressure strip galaxies seem to have an active black hole, an AGN, in the center of their galaxy. And the thought is that as these galaxies are sort of falling and the gas is being compressed by RAM pressure stripping, it falls into the central black hole, feeding it and causing this active galactic nuclei. So there's a few telltale signs and a few interesting things that RAM pressure stripping can do to a galaxy. And one of the things we have seen, of course, is that a lot of the time it's in higher mass clusters. We know this because they have a denser intra-cluster medium, which means that helps facilitate ramp pressure stripping. However, from what we just saw before, do we see this often in groups? And this is work by Tutku, which has been submitted semi-recently, and hopefully, fingers crossed, will be on the archive very soon. So for this work, we took the same field, that gamma field from before. We took the overlapping data from the HyperSuPrimeCam. This is a very large telescope with beautiful image quality to look through all of the groups that we had previously and find new potential RAM pressure strip galaxies. Here are a few examples. So all of these galaxies were visually identified by Tutku herself, as well as a couple of others to verify these ones. And we sort of ranked them as being secure candidates where everyone really thought there were strong candidates and they had definite RAM pressure stripping signs, or tentative candidates when only one or two of us saw features of RAM pressure stripping. So the images here on the left are the G-band image from in the black and white ones, and the right ones are the 3-color GRI images. And what's very interesting is that a lot of these galaxies, despite being in groups, look very, very similar to those in clusters. They have, as similar to the cluster ones, they have a high star formation rate. We can see that in the right-hand side figure. So they have that elevated star formation rate compared to other cluster or group galaxies. They have similar stellar masses and similar colors. They look very similar. The only difference is many of these galaxies are in sort of groups or halos that have a very low halo mass. So many of them are sort of below that 10 to the 14, which is sort of very interesting. So they're sort of the same looking things, but they're in lower mass halos. So we found that the fraction of RAM pressure stripping galaxies compared to the amount of star forming galaxies on the whole is about 6.5%, or if we only take the best ones, those secure candidates, it was down to about 2%, which is lower than what we see in clusters, but is actually consistent with other works that look in galaxy groups, such as this work, Roberts 2022. So this suggests that groups can definitely host RAM pressure stripping. Now we find that if we were to model gas stripping using a galaxy group based with the different velocity dispersions based on a Vera-Franken-White profile, and we sort of let a galaxy of a certain stellar mass and a certain gas disk ratio fall into this, that even in very low mass groups, so if we take a group of only 300 kilometers a second and a very high mass galaxy with a lot of ability to retain gas, such as 10 to the 10.5 in this green curve, if you move very close to the group center, we can still see that the gas will be removed. So it will remove a lot of the gas if you get really close to the center. Now, it's obviously not as efficient as something like the orange curve in a larger cluster with a lower mass galaxy, but groups can, not as often, and as we saw from the fractions, not as often, but can still quench galaxies. Now, an interesting quirk, or not a quirk, but an interesting result that sort of goes with this is if we look at the tail angles. So if we look at the debris behind the galaxies as they fall into the cluster, we can sort of figure out when they might have experienced this RAM pressure stripping. So when we talk about a tail angle, I've got a little schematic here on the left, which shows sort of this tail offset from the BCG here, where 180 degrees is a tail pointing directly away from the center of the group, and a tail offset of 0 degrees is pointing directly towards the group. And in clusters, what we see is that most galaxies tend to have their tails pointing away from the cluster center. So the tail orientations tend to be away, so 180 degrees. However, in groups, both in our work here in the middle panel and in this work from Roberts et al. 2021, we can see that the galaxies sort of have a peak actually pointing towards the center. And this suggests that the galaxy hasn't experienced RAM pressure until it's almost very close to the BCG, and as such has sort of gone past the BCG when the tail is formed, and such that the tail is pointing towards the center instead of away from the center. So that's a nice little thing we see in the groups that we don't see as often in the clusters. So that might be sort of further evidence that these galaxies in groups still have RAM pressure, but it sort of acts later and closer to the dense cores, and they're not as often further out compared to the large clusters. Now, those results we had before we're sort of still very, I mean, they're going to be published hopefully very soon, but they're still very preliminary and only based on a few members. So we've sort of only got, 15 or 10 galaxies in this plot that you can really get tails of that are secure candidates. So the best galaxies we haven't got a lot of them. And so a lot of the results we really want to look at, we want to try and get a lot more galaxies. And so we're hoping to sort of find new RAM pressure stripping candidates to try and sort of see if we can understand galaxies on aggregate, on mass, if you will. Now, the problem with doing that is that a lot of the time jellyfish are found through visual classification, sort of eyeballing them. The ones from Coutu et al., we visually classified with 3 of us. There were several authors who did that, and a lot of the studies to date have done similar. There have been some efforts previously to try and use automatic or proxies for morphology to find them. So we've got here work on the left from McPartland that found that jellyfish and RAM pressure strip galaxies in the blue tend to have specific concentrations and asymmetries. And similar here from Roberts et al. 2020, we see that the Gini and M20 coefficients of the stars, which are the jellyfish galaxies, tend to lie to one side. But these are still sort of very scattered and often can confuse jellyfish galaxies with mergers and tidal interactions. So we need to see if we can find some other sort of morphological proxies. And the one I'm interested in is using Galaxy Zoo. And so the question I'm sort of asking is, can we use morphological properties from citizen science projects to identify signatures of RAM pressure stripping? To do this, I've taken a catalogue of 212 galaxies with RAM pressure stripping. So I've taken them from all different sources and as many places as I can. I actually assembled a sample of over 900 galaxies, which I then matched to the Galaxy Zoo catalogue, which yielded 212 galaxies, which overlapped in terms of the footprint and the appropriate brightness. Now, Galaxy Zoo 2 is a bit more in detail than the original Galaxy Zoo, which just asked, was it a spiral or was it an elliptical? Galaxy Zoo 2 asks things like, is there a bar? How tightly wound are the spiral arms? And is there anything odd? So armed with this sample of 212 galaxies that have morphological classifications from citizen science, we thought to ask, can we learn anything from this? To do this, we first have to create some sort of comparison sample. The jellyfish galaxies are clearly not going to be the same as the overall Galaxy Zoo sample. We can see this here in the plot, the cumulative histogram of absolute R magnitude. The black line of the full Galaxy Zoo is quite divergent from the purple line of the 200 known jellyfish that we're interested in. So what we've done is we've created magnitude and redshift matched control samples, one that includes galaxies within clusters and one that includes galaxies within fields. So these have got 8 matched magnitude and redshift matched galaxies for each jellyfish, such that from the 200 odd jellyfish galaxies, we've got about 1,600 sort of comparisons of which we can use as a baseline to test. So now armed with these 2 comparison samples, one in clusters, one in the field, we can now see if there's any differences between jellyfish galaxies and these comparison samples. Now, for one caveat, I will note that the Galaxy Zoo did use SDSS imaging, and that is very shallow. So I've got here 2 images of known jellyfish galaxies. The right-hand images show the image from Legacy Survey or the Decals survey, and the left shows the SDSS, the corresponding SDSS image. The SDSS image is what the Galaxy Zoo classifiers will have tried to use, and so they won't have seen some of the fainter features you can see in the deeper imaging. So a lot of these results come with the asterisk that a lot of features may be too faint to actually see. However, we see there's some really nice results that come straight out. So if we look at the galaxies, the jellyfish galaxies compared to these comparisons, we see a lot more disks in the left-hand histogram. Straight away, we can see that a lot of these galaxies have disks compared to your average cluster or field comparison galaxy. And additionally, when voters were asked, is there anything odd about this galaxy? The classifiers all said, yes, we see something very odd about this. So we can see that while most of the galaxies in clusters and fields were not odd, there's a significantly higher odd fraction for the purple line you can see here for the known jellyfish galaxies. Furthermore, there was a question asked, what kind of odd feature do you see? There were answers like, do you think it's irregular? Do you think it's disturbed? Do you think there's a dust lane? Do you think this is a lens? Do you think this is a merger? And we find that a lot of the time, for the galaxies that were considered to be odd by these citizen science classifiers, they found that these galaxies were irregular or disturbed. So this is sort of the histogram combining this irregular, disturbed, and the other category. Compared to those samples, again, they seem to be more disturbed compared to the other ones. What's also really reassuring, and might be a bit different to some other automated methods, is that the classifiers didn't consider the mergers. If you have a look on the right-hand panel here, we see that the fraction that these galaxies are likely to be the odd feature is a merger is actually very low. We actually have a very large peak sort of in the lowest bin, so that very few of these people actually thought these are mergers. So it's really nice that these citizen science people clearly can see the difference between sort of these RAM pressure stripping features and potential merging features. Now, I will also note that this sample I collected had galaxies that were selected with optical wavelengths or H alpha imaging, but also some that were found with radio imaging, such as through LOFAR or through their neutral hydrogen gas. Now, not all the galaxies are going to be the same, and when we just divide the sample into optical only versus the radio ones, we can see that very quickly the odd fraction changes. And that while many galaxies that have optical signs of RAM pressure stripping are quite odd to these classifiers, many of the galaxies that have the radio jellyfish signatures do not seem to have those features. So it's important that the galaxies we find through citizen science, these would be only through optical, and that would not be necessarily contain galaxies that experience RAM pressure stripping that we can see through other mechanisms. So it's important to see that it's not always the case that if a galaxy has an optical deformation, it'll have a radio one, it'll all be in the same. So it's very interesting to see that. Now, we've seen that these galaxies seem to have some unique features about them. These classifiers seem to think of them as odd, they seem to think of them as not being a merger, and they seem to think of them as sort of being irregular or disturbed. So the question I then ask is, if I take a random sample of cluster galaxies that have Galaxy Zoo data, and I select the ones that have this, that are odd, that are irregular, that are not mergers, will I be more efficient at finding RAM pressure stripping galaxies than if I just pick random other cluster galaxies? And the answer, tentatively, so this is still vaguely ongoing work, is that yes, we do. So having a sample of about 320 galaxies with Galaxy Zoo that we've selected to be odd, to be irregular, to be not merger, and if we have the same number of galaxies that are just cluster galaxies without any thought to a Galaxy Zoo flag, the number of jellyfish we found when we got experts to sort of go back and classify and look for jellyfish galaxies was about 1.5 times. So we got 26% found jellyfish features in our sort of Galaxy Zoo flagged ones compared to just random comparisons. So we're now seeing that using sort of citizen science questions, even if it is just, is this galaxy odd, can really help us in finding these RAM pressure strip features, which is really nice for us. Additionally, this has given us 141 new candidates. So these 4 here are examples of new potential RAM pressure stripping candidates that we can use in the future to investigate and understand RAM pressure stripping. So now that we've seen that there's that citizen science definitely works and that asking these questions can help sort of isolate new possible RAM pressure stripping galaxies, we can hope to sort of get their opinions on these in the future. Now, one nice thing is that in existing Galaxy Zoo, so the main Galaxy Zoo thing, they have a tag section where you can literally like hashtag jellyfish to be that literal. So you can put in a hashtag on these galaxies with certain features. So these 3 images here you see are 3 images of galaxies in the regular Galaxy Zoo that a volunteer in the Galaxy Zoo project has actually seen something that they thought this is worth, hashtag jellyfish. So we can see further evidence that these citizen scientists, that members of the public, are able to pick out these features and sometimes even classify them as jellyfish galaxies. So these are 3 new jellyfish galaxies that have never been sort of catalogued or done before, which were found through citizen science and not through any other methods. So that's really cool that we can see that. So using all this information, what we're hoping to do is to start a new sort of Galaxy Zoo project. And this is Galaxy Zoo, sort of Jellyfish Galaxy Zoo, if you will. So this is something that is being led by one of my colleagues, Callum Bellhouse, in INAF in Italy. And this is hoping to launch in a few weeks. And what we're doing is we're getting galaxies around vague clusters in the sky, and we're just going to ask, do you see jellyfish features, and what kind of jellyfish features do you see? Now, we're working on this. Currently, we've got beta testing in English, in Italian, and Spanish. But speaking to Callum last week, we're actually getting some of our Brazilian colleagues to also include Portuguese. So we're hoping that soon we'll have an extra language when we can release the thing. So if you're interested, or if you know anyone, it doesn't matter if they're a scientist or not, because that seems to be fine for finding these things, who would be interested in this, we're going to be hopefully launching this soon. And it's going to be launched in both English and Spanish and Portuguese. So if anyone you know is going to be interested, please stay tuned. Anyway, that's all I have time to talk about at the moment. So thank you very much for listening. I'll leave you with my conclusions here, and I'm happy to take questions. Thank you very much.
Okay, Jacob, great talk. Thanks a lot for this talk. And
would you like me to stop sharing screen, or?
As you want. If you would prefer to see our faces, maybe it's nice if you, then in case you need it, you can just...
Yeah, will do.
Yeah.
Yeah, I do really want to see other people's faces. It's weird to present with no faces.
Yeah, it's better. So let's start with the questions. I think the first is Laert. Please, you can ask your question. I think you are mute. He knows.
Do we need permissions to let people?
Okay, now I have permission.
Okay. Sorry, I didn't know we could do that.
Yeah. Well, very nice talk, Jacob. I have two questions. The first one is that apparently you are enlarging the concept of jellyfish galaxies, in the sense that all galaxies that have, say, a tidal feature seen in the young population can be classified as jellyfish. Is it true?
I mean, so what counts as a true jellyfish galaxy is a question and an ongoing debate, I think, that will probably not change. I apologize that I may have used the word jellyfish galaxy very liberally in this talk. I guess it's potentially a bit rude, but it was a bit showboaty because it's a good catch-all, and it's a really good outreach term. If you were to speak to people who are not scientists and you say, I study jellyfish galaxies, and they say, what are they? And I show you a picture, they go, it looks like a jellyfish. It's a really great outreach term. But you're right. For some people, a jellyfish galaxy sort of requires that, not just a visual classification of some sort of deformation optically, but has the
kind of tail.
Sort of the tails in H alpha and not the stellar body and things. So there are some people, there are some groups, especially those in the GASP survey, who've got strict definitions on H alpha tails being certain lengths and things for the sort of a jellyfish phase. Now, I don't think necessarily it's going to be a definitive thing, but that's sort of what the correct term looks to be with at least that group, and it's probably different for different groups. And so I try, and hopefully in the text, at least of the talk, you saw that the word ram pressure stripping candidate and galaxies is probably more general, because you're right, like a lot of these galaxies may have tidal features in it. Mm-hmm. Yeah, we tend to try and look for unilateral, whereas a gravitational will sort of contort both sides a bit more. But yes, absolutely, it can have contamination. So jellyfish, while being a purist term, is probably not the best term for all of these.
Yeah, anyway, I think that it is interesting to enlarge the concept of jellyfish to include objects that suffer ram pressure in some way. My other question is the following. These are transient phenomena. And if we say it happens in a given galaxy now, for how long are you able to detect the jellyfish phenomenon?
So that is still an ongoing question. I know that a lot of the, so I think depending on exactly what you are talking about, the timescales can be different. I think the gas itself is sort of stripped on the scale of a couple hundred mega years. The time it takes to change the whole galaxy body, so maybe make a galaxy from sort of blue to red, I think can take up to a gigayear, so sort of a whole crossing time of a cluster. If I'm remembering that simulation work correctly, apologies if I've got that a little bit wrong. Additionally, the tails themselves can sort of have different lifetimes depending on how much gas there is. There's some work that possibly is actually out this week by Rory Smith, who's actually simulating sort of the lifetime of tails as simulated galaxies sort of enter a cluster based on a few of these sort of assumptions. And that's work from Rory Smith. I can't remember what kind of mean he found for it, but if it hasn't come out on the archive yet, I think it will very, very soon. And that sort of looks at these lifetimes. And I think half a gigayear was the number that's coming to me. It's, I mean, I apologize, it's a bit of 4 in the morning, so it may be wrong, but I think that was about right. But yeah.
Okay, thank you. Very interesting talk.
Thank you very much.
Okay, thank you. Now, Gaston, you can ask a question.
I like it very much. I like this citizen science use to classify jellyfish galaxies. And I had the same question as Laerte. I was wondering how you could separate tidal effects from run pressure when looking at the jellyfish galaxies. Because some of the galaxies that you showed, looking at them, I couldn't decide if they were run pressure effect or some tidal effect. And I was wondering if it matters.
So, well, for all the ones I showed coming through, the consensus is by the papers that they were published in, or through me and the co-authors of the work we're doing now, that this is due to ram pressure and almost certainly not tidal interactions. Now, you know, how much can we trust one, like this group word and stuff, and you're never going to fully know. There are a few telltale signs that we look into specifically that sort of help us. Some of them include sort of specifically deformations on one side of the galaxy, whereas it's rare that an interaction will not sort of symmetrically hit a galaxy. These sort of one-sided tails, and specifically like the word tails is something that really seems to only come about through ram pressure stripping. But what we do, I mean, what was really nice that we saw is that if we take as gospel these galaxies as ram pressure stripped are not tidal or not undergoing that, it seems that the citizen science people seem to be able to tell that. They can tell that this, well, their opinion seems to be that this is not a collision, this is not a merger. That they seem to think of this is odd, but this is not due to what I consider to be that. So again, as I said sort of before, I would be hesitant to call many of these galaxies true ram pressure only galaxies without, you know, looking at the kinematics, you know, through stuff that the GASP survey does with MUSE to fully determine that. But from what we've seen, one, the features we pick out, this sort of unilateral, these tails on one side, and also there's a couple other features. I won't get into them too much, just because there's a few different ones you can look at.
Okay, thank you. May I ask another question?
Yes, please go ahead.
Okay, it's earlier in your talk, you were separating the groups in overluminous and underluminous with respect to the optical emission. And I was thinking, many groups that are dominated by elliptical galaxy, well, these elliptical galaxies, usually they have an AGN in their center. So they have a point-like emission in X-rays. And I was asking myself, could this bias the results? Because
So the answer is we think we're pretty confident with not having strong AGN contamination. So there's a few reasons for that. Firstly, the XXL group, the people who run the XXL survey, they're interested in AGN science. So they've actually got a list of all of the point sources that they can find and model, and they have sort of taken them out of the survey. So we've got a list of all the point sources, and then when we take our apertures, what we do, I glossed over this because it's sort of the down and dirty details, is when we take our aperture, if there's any point sources known to be in those fields, we actually mask them out. We mask them all out, and then the posterior distribution is sort of updated based on the change in area. So we've actually taken out a lot of the smaller point sources out of those. So that shouldn't be the case. Now, there is a case where you can have some very faint AGN, which might look a bit fuzzy and not very point sourcey and hasn't been picked up by the algorithm. But we don't expect those to be prevalent in any of the subcategories, because we don't expect those to necessarily be in any of the subcategories, and as such, bias our results. Like, they should be self-consistent, because we're sort of trying to get rid of them all in a consistent manner. And as a sort of a proxy test for this, we actually looked at the fraction of AGN. So we looked at the star-forming fraction, the blue fraction, and we actually looked at the fraction of AGNs optically, not through the X-rays this time, and we didn't see a trend. There was no trend across our samples of BPT classified AGN. So at least in that sense, we didn't see AGN. Now, there's more we can probably think of, and there might be some hidden in there, but we did what we think is a pretty comprehensive job at making sure it's not a big thing.
Yeah, okay. No, the problem is that the X-ray survey was done with XMM. So the problem is that XMM sometimes some point sources appear like extended sources.
Yes.
That stuff is not that good. But okay, but we compare it with different methods and use a homogeneous way to detect them. So okay, thank you.
Yeah. Good.
Okay, thank you. I have a question from someone in YouTube. It's Pedro Enrique Cesar. He's asking, I'm sending it in the chat in case you wanted to read it, but it asks, how do you interpret the AGN triggering in jellyfish? They are like gravitational instabilities that make the gas flow to the center. There is some evidence of AGN feedback in jellyfish galaxies.
So there was a paper in 2017 which found that it was a sample of like 7, but it was like 5 of the 7 galaxies that were strongly stripped. So not just ram pressure stripping galaxies, but confirmed with Muse and very strong tails. So we're talking like really long, really spectacular cases of ram pressure stripping, the true jellyfish, if you will, had an AGN in the core. Now, 2 sort of scenarios naturally present from this, one of which would be that the ram pressure stripping is causing gas to sort of funnel in, or like to be compressed, because as the galaxy is coming into the cluster, the gas sort of gets compressed, and this can sort of fall onto the central AGN and then feed it, causing this AGN to sort of shine bright and feed the black hole to be an AGN. The alternative, I believe they postulated, is that the ram pressure stripping, the gas, the H alpha gas you see, is actually being sort of excited, and it helped to be released by an already AGN. Now, their interpretation, and I believe this interpretation has been, now I don't know, again, 4 a.m., it's not the best time to be quoting papers that I've read a few years ago, but there's simulations from, I think, Ricarte, I believe the author is, with simulations looking at this kind of thing as well. And between the first paper of Foggianti, another paper by Giorgio Palusso, and then this simulation paper from Ricarte, seem to show that the favored idea is that the ram pressure stripping is causing the AGN to sort of be activated, if you will. And there's a few ways they test it. I know that in the Poggianti paper, they look at the location in phase space, i.e. where it is in falling into the cluster, and that these galaxies are often very close to the center, but are moving very, very fast. And as such, they're experiencing as much RAM pressure as you're getting. So it's unlikely that the AGN's helping the RAM pressure exist, but the other way around is probably more likely. Again, the details are found in those 3 papers, so I apologize I don't have more details on it, but hopefully that helps answer the question.
Okay, thank you very much. I hope that answered the question of Pedro. So we are still tuning in the YouTube in case Pedro wants to ask anything further, and let's move on with the batch.
Oh, hi. Very interesting talk. Thanks, Jacob. Yes, I have a question in this regard, the AGN, the role of the AGN in these jellyfish systems, because you said that, okay, if you look into the self-formation rate and the other parameters, other observables, you do not see a final trend. Nevertheless, you did identify this angular distribution of the tail, right? And then you said, okay, when there is evidence of a central galaxy with an AGN, we do see that this angle is smaller because of the distribution that you showed seems to indicate that there is a trend there, a difference in the tail distribution when you have this central mass, the central galaxy with an AGN. Is that so, or did I misunderstand that diagram that you showed with that angular distribution of the tail? That's a way to identify these morphologically these systems, right? The jellyfish systems.
So this might have been me skipping over a little bit too quickly. So the idea of the tails and the tail directions is just looking purely at just, do we see these galaxies early in their infall, i.e. as they're still coming into the cluster, right. Or if they've gone sort of through the center.
Exactly.
We haven't got necessarily a correlation between how the tail looks and an AGN. So we haven't presented it with the AGN. What the comparison was with the large clusters where all the tails are pointing away. So in the in the big clusters with a strong intra-cluster median, we see that the tails are generally pointing away from the center of the cluster. Mm-hmm. And in the groups, in the lower mass halos, we see that the tails actually point sometimes towards, because the galaxy, as it's coming into a group, it's sort of come in, hasn't experienced RAM pressure until late, and then it's gone past pericenter. And that's, I mean, it's tentative results still. It's still low number statistics, as I sort of alluded to before. But we seem to see that in the groups, the lower mass sort of group halos, the tails point sometimes towards the center of the group.
Right. Not that necessarily in the center you do have an AGN, right?
We haven't. I can't comment on it because I haven't looked into it. It could be an interesting thing to see because, I mean, there's a few questions we've had on the AGN in RAM pressure strip galaxies, and there's actually, so finding these new candidates, finding these new ones with these galaxies surveys, what I'm hoping to do is investigate this link between RAM pressure stripping and AGN in big samples. So as I said, that Poggianti work is 7 galaxies, and we've got Giorgio Peluso who's done about 80, but I'd like to get 1,000 and really have a look. You know, do we see this link between RAM pressure stripping and AGN en masse kind of thing? And where in the infall do we see it? Like, do we see it as they sort of start to go in, or is it later on? When does it get triggered? So this is actually questions I'd love to answer, but at the moment we're still compiling those large samples. So I very much appreciate the question, but unfortunately you're a little bit too early for me, so I'm sorry.
Okay, no, it's fine. Thanks a lot.
Thank you.
Okay, so just to inform you that Pedro from YouTube says, thank you very much. That helped a lot, the question.
I'm glad it did, thank you.
So I have a question myself. You mentioned that you had 141 new candidates, Jellyfish Galaxies candidates from this citizen science project, let's say, how many, how was your sample? How big was the sample?
The sample was about 600 or so. So,
okay.
So we picked I think it was 314 or some, let's call it 320 for numbers that are easier in my head. 320 odd galaxies that we had Galaxy Zoo flags for. And we sort of said, make them odd, to make them not merger, make them irregular.
Mm-hmm.
Give those to us and we'll look at those, we'll classify those. And then for each one of those, we took one random cluster galaxy as sort of a comparison. So we've got 320 of one, 320 of another, so 640 in total. And of those, we found 141, and of which we were more efficient in the Galaxy Zoo flags, so we were better at finding them there.
I understand.
And this comes back to the first question and stuff of, when is it a round pressure stripping candidate? When is it a proper jellyfish galaxy? So there's different degrees, and we've got some that are, just mildly have a bit of a deformation that we think is maybe due to it, and some that are got a light, nice stripping sort of look. So, it's 141 candidates of all kinds of shapes and sizes that may or may not be the most. So, yeah.
And now a question that I was wondering if can you use these results from the citizen science to train a learning algorithm, like do something related to that now that it's very currently is really emerging this using machine learning in astronomy.
So a lot of what we're doing is actually, the idea is to sort of be a precursor. And I think there are a couple of talks online from Chris Lintott, one of the main founders of Galaxy Zoo, expressing how you can sort of use this citizen science in conjunction with these machine learning algorithms to sort of get the best of both. Sometimes the combination of man and machine works actually better than one or the other on its own. Now, I'm not a machine learning expert, but while I know there are certain CNNs, so convolutional neural networks and stuff, and adversarial and unsupervised machine learning networks that can maybe find these kind of features, the best and most robust ones that I believe we're looking into tend to require large training sets. So a lot of them use, I think it's like 10 to the 4, so about 10,000 odd is about par for the course as your training sample before it can go through and look at it. So the limitation on that is that we haven't got 10 to the 4. We've just hit 1,000. So we're we're a factor of 10-ish, too low. Now, some of the advances suggest that we can probably get away with having low, but the reason we were doing this is when we started looking for these galaxies, we were only at sort of a few hundred, less than 600 and stuff. So we need to build up that sample to let the machines take over, kind of thing.
Yes, I understand. Yeah. As you mentioned, this can be the precursor of in the future to get to a big enough sample.
Exactly. And we want to have a big enough sample such that when things such as the LSST at the Vera Rubin Observatory come online and things like that, it might be easier that these things can be just done sort of algorithmically.
Exactly. It would be already preset, let's say, with all your experience on this.
Yeah, and that's sort of the hope with looking for these things, that we can have a sample that, for that kind of thing, we can do the more automated way.
Yeah. Okay, we have another question from Marcelo. Please go ahead.
Okay, can you hear me?
Yes.
Okay. Hi, Jacob. Thanks for your talk. Very nice work. I'm trying to put things together here. Please tell me if I'm wrong. When you was talking about the galaxies in falling groups or clusters, it seems to me that room pressure stripping depends on the density of the environment, correct? And the velocity squared.
Yes.
And when we are thinking about clusters, if the galaxy is in falling a cluster with a low impact parameter, I think the process is very fast, and maybe it's harder to find jellyfish galaxies or galaxies suffering ram pressure stripping in clusters in this case. And so it seems reasonable that when a galaxy is falling in a cluster, it seems more comprehensible that this galaxy, the jellyfish galaxies, has a higher parameter impact, and it's somehow in the outskirts of the cluster. And that's why we are seeing the tail of the jellyfish back on the back of the cluster. And when we are talking about groups, the process is much lower, less fast. So it's possible to get the galaxy pass through the group, and still the ram pressure is occurring. Is this sound correct, or?
Yes, I think so. There is a few complications, as you say, with the impact parameter, and also things. Now, these are simulations that I don't have good references for. I think Elke Rodinger might be one. You can change things such as the orientation of the galaxy. So if the wind's going face on or side on, like, does that change how much is being stripped? Because, you know, if you're getting the gas all in the face compared to on an edge, that also changes it as well. But I think the main thing of, yes, the galaxy as it's coming into the cluster does get that strip, versus in the group doesn't happen till right close to the center, which is why it happens there. That yes, I think that sounded okay.
No, hey, okay, nice.
And then, yeah, there's, as I said, a few complications with those things with orientation and impact parameter and stuff. Yeah.
Okay, thanks.
No, thank you.
Okay, thank you very much for your questions. Let's see if there's another more question in the YouTube or here. I think no. So I'm going to thank you very much, Jacob, for your talk and for being at 4 a.m. giving this talk. So a special thanks for you. Would you like to say something before we end the transmission?
No, just thank you very much. It was really exciting to give this presentation to you all, and some really interesting questions, and a lot of things to think about, I think, from a few questions that I didn't have the answer to about AGN. So I'm excited to continue working on those things and hopefully come up with some answers for you another time.
Okay.
So thanks again.
Thank you. So Richard, whenever you're ready, please.